Hi, our last speaker of the day is Maryna Viazovska. Maryna got her PhD in 2013 from Bonn on modular functions and special cycles. And after that, she did a postdoc at the Berlin Mathematical School from 2013 to 2016. And in 2016, she made a really amazing discovery about sphere packing. In a great breakthrough, she solved the sphere packing problem in 8 dimensions with a wonderfully simple argument. So we're very lucky to have her today to tell us about it. Please welcome Maryna Viazovska.
So thank you very much. I'd like to thank organizers for inviting me to this conference. And so today I will speak about sphere packings, Fourier interpolation, and modular forms. So let me start with the sphere packings. So what is a sphere packing? So here's the definition. So it is exactly what it sounds. So we have a d-dimensional Euclidean vector space, and in this vector space we consider balls of equal size. And so now suppose we want to pack balls of radius 1, then we choose a set of points such that distance between every two distinct points is at least 2, and then we consider a union of open balls with centers at these points, then these balls will not intersect, and then we say that such a union, it is a sphere packing. So now what we would like to do, we would like to, among all the possible sphere packings, we want to find those which have the maximal density. So for this, let's define what is the density of a sphere packing. And so first, let's define what is a finite density. So we have our packing, so now we take a very big ball with a center at 0 and intersect our packing with this ball. Then we can divide, then this, the volume of this intersection would be some finite number, so we divide it by volume of a ball, and we obtain a finite density which will depend on this number r. So now what we would like to do, we would like to take the radius r to infinity. So unfortunately, we can think of some pathological configurations where simply such a limit would not exist. So our configuration could be very irregular. But what we can always do, take the limit supremum of all such densities, and then the number which we obtain, we call it the density of our packing. So now the question is to find the supremum over all possible packings. So what do we know about this constant in different dimensions? So this is what we know about small dimensions. So in dimension 1, the sphere packing problem is trivial, and the sphere packing constant is obviously 1. So in dimension 2, the problem is a bit more complicated, but still, even bees can solve it. So we see here a hexagonal packing, and it covers, so such balls, they would cover almost more than 90% of the area. And in dimension 3, the sphere packing problem is most famous, and it's known as Kepler conjecture. So here is the picture from Kepler's manuscript, where he thought about best possible arrangements of spheres. And he conjectured that the best density we can achieve in dimension 3 is this number, which is about 74%. And so this is what we know about, so maybe another thing I wanted to say, that all these problems, they're also now rigorously solved. So this problem, it was solved still at the edge of 19th and 20th century by Axel Thue, so he was the first one who gave an argument for that. And the Kepler's conjecture was famously solved by Thomas Hales. And so this is what we know. What we know in other dimensions are the lower bounds, which come from some known configurations, and upper bounds, which are obtained by the methods I will discuss a bit later. So here we see that somehow the upper bounds and lower bounds, they meet only in 5 points. So for 1, 2, 3, for 8, for some reason for 8, and for 24. So today I will speak about these two big dimensions, about 8 and about 24. Okay, so good question. So, of course, somehow plotting the density, the sphere packing constant, it would drop exponentially, so drawing it is not very convenient. Therefore, this plot, it is normalized in such a way that we take our packings, our configurations, to have center density 1, so not the so it means that, roughly speaking, 1 unit of a volume will contain 1 center of a ball from our configuration. And then if we fix this center density, what we can vary would be the radius. So this would be the maximal possible radius of a balls with this center density. And then it seems like, roughly speaking, it would grow like a square root of the dimension, up multiplied by some unknown constant. So what happens in these special dimensions 8 and 24? So first, in these dimensions, we have particularly nice configurations of spheres, very nice candidates for the solution. So in dimension 8, we have a special lattice called the E8 lattice, and the name E8 comes from the fact that it's a root lattice of a E8 Lie group. And so this, this lattice can be written explicitly in the following way. So just by giving coordinates of its vectors. So it will consist of all vectors such that their coordinates are either all integral or all half integral. And moreover, these coordinates have satisfied the following congruence. So if we sum all the vectors, we will get an integer number, and this number will be also divisible by 2. And so what happens is, so this is a unique lattice, which is, so somehow the word positive definite means that it's a positive definite quadratic form, which maybe is not so somehow is obvious. Then it's even. It is. It means that all the vectors in this lattice, if we take their lengths, they would be square roots of even numbers. And it's a unimodular lattice, so it means that the center density of roots in this of points in this lattice would be 1. And from a mass formula, we know that there is only one such lattice. And so, because it's an even lattice, it means that minimal distance between 2 points in this lattice would be square root of 2. So if we consider now balls with radius 1 over square root of 2, we will obtain a sphere packing. So other way would be to take this lattice and multiply it by square root of 2, then we can pack unit balls. And so the theorem I would like to speak about today is that there is no packing of balls in 8-dimensional vector space, which has a density greater than the density of the E8 lattice packing. And this number is about 25%. So as I told you that with dimension, the sphere packing density, it drops exponentially. And in dimension 24, we also have a special configuration, so-called Leech lattice. So in this lattice, again, it is even, it is unimodular. And so now in dimension 24, we have 24 such lattices. So it's a result by Niemeyer that exactly 24 lattices satisfy this equation somehow up to isometry. And but among these 24 lattices, there is only one such that the minimal distance is not square root of 2, but is equal to 2. And of course, already this condition makes it a good candidate for a sphere packing. So now, in this case, we even don't have to rescale our lattice. We can just pack it with unit balls, with centers at this lattice. And so this is a theorem which we proved in collaboration with Henry Kohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko, is that the greatest possible density of a sphere packing in dimension 24 is the density of Leech lattice. And it is about this number, which this time is much smaller. And even so, it's still very big for dimension 24. And so now I would like to explain you how did we obtain this red line on my previous graph, which told us the upper bound. So at the moment, probably the most successful method for proving upper bounds for sphere packings in big dimensions is linear programming. And so how this method works, so here is a theorem by Henry Cohn and Nam Elkis, which was proven in 2003. So there is the idea is not to study the geometry of a lattice, but instead study harmonic analysis. So their method tells us that if we can find a function in d-dimensional space which satisfies these restrictions, first that this function it is non-positive outside of a ball of some radius r0, then the Fourier transform of this function is non-negative, and our function will normalize it in such a way that the value of a function is 0 is equal to the value of its Fourier transform at 0, and it's equal to 1. And whenever we can find such a function, then we know that every sphere packing in this dimension has density which is bounded by this number. So volume of a d-dimensional ball of radius r0 divided by 2. And so the proof of this theorem is surprisingly easy. So here I will give you the idea how the proof goes. So suppose that X is some configuration of points in the dimensional space, and the distance between any two distinct points is r0. So here I will not prove it for arbitrary, I will not consider arbitrary set X, but instead I will consider a periodic sets. So we will think that there is some lattice L, and this lattice can be very big, and such that our configuration is periodic with respect to this lattice. So this will give us, so what we'll do, we would like to, so if we want to compute the density of our sphere packing with centers at the set X and radius r0 divided by 2, then it is essentially the same as estimating this number, so number of centers of this set, modular the action of the lattice L. So now we use the special properties of our function. So here in the first row, we use the property that our function is non-negative, non-positive for all vectors of length bigger or equal than r0, and use this property of a set X. So the next step, we just rewrite this sum in a more symmetric way with respect to X and Y. Sorry, so this should be Y. Sorry, there's a typo here. Oh, no, sorry. Okay. And so now, next step, what we do, we use the Poisson summation formula. And so the next step is a following trick. So now what we do, we will rewrite this double sum as an absolute value of a simple sum. Now, after we have done this, we see that all these numbers, they have to be non-negative. So we can use the second property of our function f, so that its Fourier transform is non-negative everywhere. So instead of writing this big sum, we can consider only the summand which corresponds to m equals 0. And we obtain such an estimate. So now when we compare this number to this one, we of course can get the estimate for the sphere packing density, or rather for the center density of this set X. And so this method seems to be quite wasteful, because you see what we have done here. So here we neglected many terms of our double sum. And also at this step, we have neglected many, many terms. So it seems like we will always get some estimate, but we have little hope that this estimate would be actually sharp. However, so Kohn and Elkis discovered that in dimensions 8 and 24, the bounds they could obtain using this method, they were extremely close to the densities of existing packings. And so what will I speak about today is that to show that these somehow numerical zeros, they are actually mathematical zeros. And so we will show that there exists a radial Schwarz function which satisfies these three conditions. So it satisfies somehow the optimal possible conditions. And so, and the similar result we also proved for dimension 24. So we also found a function which satisfies all these three conditions, only here the length of this ball outside of which our function is non-positive has to be changed. So now, here is a plot of the function f and f hat. So here, just so the function would look nice, I multiplied by this factor so that it would not vanish, would not become invisible very fast. So here, I would say some observations which help us to search for this function. So first, we can assume that our function is radial, so that the value of function at some point depends only on the length of this point, of the distance between this point and 0. And so we see that all the conditions in the theorem of Kohn and Elkis, they are all rotational invariant. So if we can find one function which satisfies all the conditions, then we can average this function over the orthogonal group, and we will get a radial function. And of course, it's much easier to search for radial functions than for functions defined on 8-dimensional or 24-dimensional space. So another observation is something what we can see from the previous plot, is that our function and its Fourier transform, they both have many zeros. And so why do they need to have all the zeros? They need to have all the zeros so that all those terms which we neglected in our proof, they have to be 0. Otherwise, we would not get the correct bound. And so here's another way how we can see this using, again, the Poisson summation formula. So from here, we see that all of the functions, values of function have to be 0 at all square roots of non-zero even numbers. But also we know that our function has only few sign changes, so we know that almost all these zeros, they essentially have to be a double zero, so the first derivative also has to vanish. And the next, how are we going to search for our function? So now we are going to search for what we found is that also this function, it has, so to say, hidden symmetry. And we have to search for this function in such a shape, where f would be a cycle integral over some holomorphic function defined on the upper half plane, and this function has to be symmetric in the sense which I will explain in a moment. So at the second part of my talk, I will actually explain you why should we look for our function in a shape like this, because somehow these first steps, they seem to be logical, and here it seems like it's coming out of blue, but this is something that I will explain in the second part of my talk.
So gamma is just some path.
Sorry? Gamma is, yes, okay, for us it would be some concrete path, and so here we leave for us lots of flexibility, so gamma would be some path and phi would be some function. So what I will do now I will specify what is exactly this function and what should be this path. So I've told you that our function f, which sometimes we call it somehow magic function, function which proves optimality for us. It has a hidden symmetry. And this is a symmetry not at the Euclidean space, but rather at the upper half plane. So it would be a symmetry of this function phi under the integral. So we denote by this, by H, the upper half plane, so the set of all complex numbers with a positive imaginary part. Then the group the group PSL2Z, the group of 2 by 2 matrices with integer coefficients and determinant 1, it acts on the upper half plane by linear fractional transformations. And so what you see here, you see how so this domain here, it would be a fundamental domain of this action. And what I see here, so I take all the vertical lines and consider all their images under the action of modular group. And so we would like to study functions on the upper half plane which are symmetric with respect to the modular group. So more precisely, we will study modular forms. So we would say that, I put here, holomorphic modular form of weight k for some, so we will consider modular forms not only for the group PSL2Z, but also for its subgroups of finite index, and we say that, so this modular form, it's a holomorphic function which satisfies the following conditions. So first, it satisfies this transformation rule with respect to all elements of gamma. And second condition is that we want our function to have to be holomorphic at the upper half plane itself. And also second condition, we can say that we want our function to be holomorphic at the cusps. So what exactly this means? It means that if we take any element which from this time from gamma 1 and apply this transformation to our function, we will get some periodic function, and this function will have a Fourier expansion, and we require this Fourier expansion to start with start at the point 0, so our function is not allowed to have zeros, to have poles at infinity, for example. And so if we fix k and a group gamma, then this space would be, we call it a space of modular forms of weight k and subgroup gamma, and these spaces, they would be finite dimensional. So they are nice and it's very convenient to work with them. So another kind of functions we will need, so we'll slightly relax our conditions. So we again consider a subgroup with integers k, we consider all functions, holomorphic functions, which satisfy this transformation rule, but now we relax the second condition. We allow our functions to have some poles at the cusps. So in this case, we'll denote the space of such functions as by this mk with an exclamation mark, and we will call them the weakly holomorphic modular forms. And now the spaces of weakly holomorphic modular forms are infinite dimensional, but if we will fix the possible order of poles, they still would be finite dimensional. And so it also makes them into nice spaces which we can very conveniently work with. So here are some examples of modular forms. So here is probably historically the first example. So this function is called the Eisenstein series. So here we take a summation over all pairs of integers which do not vanish simultaneously, and now just from the shape of this sum, we can see that the transformation rule of a modular form is satisfied by such a function. Also, so this sum will converge absolutely if k is bigger or equal than 4. And from this, we can easily see that this function belongs to this space. Okay, yes, so here z should be tau. You're right. And okay, so here z is correct. So maybe this tau should be z. And also we can write the Fourier expansion of such a function, and as I promised you, so it's easy to compute the Fourier expansion. So in this case, they would be this quite easy arithmetic functions. And so our previous definition, it would not work for k equals 2 because we don't have absolute convergence. However, we still somehow the convergence is not that bad, and using certain tricks, for example, prescribing the summation order for our sum, we could still get some holomorphic function in the upper half plane. So this function is now denoted by E2. And so what we can do, somehow this definition with double sum does not work so nicely. However, we can just take the same rule for the Fourier expansion, simply replacing this sum of divisors to power k minus 1. So here k minus 1 will be just 1. And so this function will not be modular anymore. However, it will be almost modular. So it will satisfy such a transformation rule. And so we call such functions, so this Eisenstein series E2 is a quasi-modular form. So here is another example, so the famous theta functions. So they are also modular functions. And now their nice properties, they will follow from the Poisson summation formula. And so here's an example of a weakly holomorph. So we had a holomorphic modular forms for the group gamma 1, so more modular forms which work on other groups. And so here's the weakly holomorphic modular form, which is a so-called elliptic J invariant. So this is a function which has weight 0, and it's a weakly holomorphic modular form with respect to the full modular group. So for example, it has a Fourier expansion like this, and this Fourier expansion appears, for example, in a monster moonshine. So now, how do we construct our function? So what we take now, we will take the one quasi-modular form of weight 0. So what it means that we take weakly holomorphic modular forms of different possible ways and multiply them by different powers of Eisenstein series of weight 2. So this is how we define a general, at least for today, how we'll define the general quasi-modular form. It would be a modular form which is in a ring generated by all modular forms and the series E2. And also we take this element phi, which would be a weakly holomorphic modular form with so of weight minus 2 with respect to the group gamma 2. And gamma 2, it's a subgroup of gamma 1. So, and it consists of all the matrices which are congruent to 1 modulo 2. And so we'll choose our functions so that they have the following Fourier expansions at infinity, and also we will bound their poles at other cusps. So then what we do, we consider a function g, which is defined in the following way. So we remember that the function we wanted to define, it had many double zeros. So this sign of r squared to the square, it will provide those double zeros. And now what we make is that for when r is bigger than square root of 2, we will define our function by this integral. So for r bigger than square root of 2, this integral will converge, and we will extend it, we'll consider its analytic extension for those r where the sum does not converge. And so what we will prove is that this function is the function we are looking for. So that it satisfies these two inequalities and also has these values at 0. So the function g itself and its Fourier expansion have these values at point 0. And so now, how do we do this? So, yes?
So you're saying that the integral is divergent if r is smaller?
Yes.
And so what are you doing when r is smaller than the square root of 2?
Then then we can extend it analytically. So it doesn't follow from this definition, but what we can do, we can somehow use this. So remember this, so here this contour gamma is like from 0 to infinity. But then what we can do, like for big R, we can play with these contours and write a different representation for this function.
So is it just an analytic continuation?
Yeah, so this would be not just an analytic continuation, but a continuation in R. So step 1, it's why we've chosen a function like this, because it's quite easy to compute its Fourier transform. Because the Fourier transform in R, it will commute with this integral which we take with respect to second variable t. So of course this happens, now we say that it's true only formally. We have to somehow justify this, but this can be done, it's not very difficult. So we can compute the Fourier transform of our function, and it is written in a similar way. So the only thing that has changed here is the sign in front of phi. So the second step would be to prove the inequalities, because now we have this function, it has double zeros at the points where we wanted it to have double zeros, but what we don't really know about this function is whether it satisfies the correct inequalities. And here we are lucky because the inequalities which we want to prove, they are satisfied not only for this whole integral, but actually they are true for this function under the integral. And so I've told you that these two functions, they are modular forms of some kind, and for modular forms in particular, we can easily compute their Fourier coefficients somehow, almost as many as we want. And also we know good estimates for those Fourier coefficients. So therefore, by brute force, we can prove an inequality like this. Then the second step would be to prove the same inequalities also for the Fourier transform of G. Somehow if we change the sign here, then the inequality will change its sign. And finally, the last step is that we have to verify this condition, which also turns out to be not very difficult. Again, we do it just from this representation, because somehow it would be the so yes.
For G itself, wasn't your inequality only like in a certain range of R?
Sorry.
At the beginning, you explained the function you were looking for.
Yes.
So there was an inequality for f and also its Fourier transform.
Yes.
But for f, it was only in a certain range.
Yes. So here actually, what happens? So it's a good question. So as I told you, like for this integral, maybe not for G bar, but for G. I told you that it would converge only for R, which is bigger than square root of 2. And then somehow when we analytically continue, it will change the sign, because somehow what will happen that this integral, it will have a pole at that point, and this sign, it will have double zero. So they will cancel, and everything will work out nicely. Yeah, so they are modular forms, and we are integrating them over this, so to say, essentially over imaginary axis. Okay, so this here it's IT here, and they are modular forms, and they have integer coefficients or rational coefficients. And so it means that at least on this path, they are both positive. And so I think now I ran out of slides for the first lecture. So maybe I will explain you what is reserved for a second lecture. So what is reserved for a second lecture is to actually explain this assumption here. So why do we search for our function in this shape? And somehow the reason for this is the following, that something what we discovered numerically is is that if we, before we were able to compute this function f explicitly, we tried to make many different numerical experiments to compute this function. And so at some point, because somehow I did not know how to optimize the roots where this function should have zeros, I thought, okay, so maybe because I'm so bad in programming, maybe I could just force those zeros and double zeros. And this is at least something I can do. And it turned out that somehow I was getting always some stable results. So if I just force these double zeros at square roots of even integers, I would always get the same function. And so this somehow led me to the idea that probably this function is simply defined by these values. So maybe I can force any values I want, and I will always get some Schwarz function like this. And actually it turns out that this is true, that the Schwarz function, it is determined by its values at square roots of even numbers, of even integers. And so this is what I'm going to talk about at the second lecture. So what we found is that we can we have an interpolation formula. So given the values, we can always reconstruct a function. And not only, so it turns out that the function is not somehow, so here we have all the even numbers, somehow values and first derivatives at the even numbers. But turns out if we take only the values of a function, but at all square roots of integers, so somehow the roots would be twidenser, then we still get this kind of interpolation formula. So this is what I'm going to talk about in the next lecture, and then this assumption, it will also explain why we should look for a function exactly in this form. Okay, so maybe you have some questions. Yes? Yes, okay, I will show you. So, yeah, so they are not so easy, I would say. And so, okay, so one of them is on gamma 1, but it is quasi-modular. It means that it is, I think it contains some terms which are multiples of E2 and E2 squared. Okay, not by these coefficients, but also what I did not write down here is that also we want certain vanishing conditions for phi, so to say, in other cusps. So here, these two equations, this equation, for example, it describes the behavior of phi at the cusp infinity. But we also want it to have it to behave nicely at cusp 0, and I think at the cusp 1. Yeah, so somehow like here the condition is so that the function which would work for our proof is then determined uniquely. But it's true that not all the conditions are written on this slide. So you have a list of conditions? So essentially, yes. So somehow then the conditions they're essentially so that all the tricks we are doing, for example, in proving the convergence of integral, all they have to work. And if we write all them down, then the function turns out that it is unique. Oh, sorry. And so this function psi, so now it is, this one is quasi-modular, but this one is actually a usual modular function only for a bigger group, so for the group gamma 2. Yes?
So I have two questions. To what extent did you, I know you described that there were sort
what extent did you use computer assistance in constructing these?
Like so, finding inverse of a big matrix.
Okay. And then I have another question about this proof sort of neglects properties of EA. It's sort of like the only property that's being used, which it does characterize EA, I guess, but is the only property that's being is the magnitude of the
Yes.
vectors. Do you suspect, or is there reason to believe that somehow properties of EA are sort of behind the surface as to why this magic function might work? Is there a reason to believe that?
Maybe. So this is something we don't know. So what I suspect, so whenever we have a configuration for which this linear programming method works, then probably this configuration is forced to have some good properties. But yeah, what is not so clear is how to formulate it explicitly. Because, for example, like in compact case, Henry has examples when he has some configuration which is somehow exactly of this type, so its optimality properties are proved by linear programming, and still it's some quite ugly configurations with no good, for example, no good symmetry group. So, yes?
Why couldn't we use this method to prove for other dimensions? Because theorem proved by Cohn and Elvis in 2013 is for every dimension.
Yes, okay, so maybe I could show you this plot. So the reason is that it seems like that method would not work in other dimensions. So you can see, so this red line here, this is essentially the line from this 2003 paper by Cohn and Elkis. So you see like here, and I'm sure that somehow the numerical computations are quite good. So this red line, it's rather close to the best what can be obtained with this method. And it's still quite far away from the blue line. And so, okay, so maybe like in very big dimensions, we can say that probably there is another configuration here, we just don't know it. But for example, in small dimensions, I think we are quite confident that the configurations we believe are the best, they actually have to be the best. And so the reason is that all those terms which we neglected in our proof, they are actually non-zero for these configurations. It means that this method cannot work, or at least like not exactly this method.
Are there some sort of easy projections onto lower dimensions, say from 24-dimensional one? Is there something nice that you can get, or some information you can get? Higher dimensional question gives you something.
So I don't think it works like this. So somehow I don't really know. Maybe there are some geometric tricks here, but I don't know them. It seems like probably it cannot be entirely true, but it's not like somehow it's not that direct. It's not that easy.
What about just monotonicity?
But somehow, yeah, okay, monotonicity. So we do know that this. So if we just take this constant delta, this seems like it's not monotonic. For example, you can see here, so like in dimension 23 and dimension 24, it's like, okay, it's not on this graph, but if you recompute it for delta D, I think in dimension 23, the best known density is actually bigger than in 24. Of course, 24, 23 is quite big, so maybe we don't know something about dimension 23. On the other hand, again, monotonicity, somehow, we know that this the sphere packing constant, it has to decay exponentially. So it means that comparing different dimensions is somehow not fair. We have to measure, to normalize our, and maybe after a good normalization, it would become monotonic, but yeah. Okay, so in dimension 4, there is a gap. It's that they do not coincide. It's simply, yeah. It's just bad plot. Yeah, maybe I should have taken like bigger scale, but yeah, there is certainly there is a gap there. So.
The blue line is sort of based on the knowledge we have of examples. So
Yes.
Is there a priority reason why there's not some other place way out where we can get closer?
Yeah, so I don't know. Maybe there is. So I somehow, if you'd like to bet, I would rather bet that it does not, but I might be wrong. I think there is no. At least I don't know such a reason. So, and there are actually people who, like, for example, there is this decorrelation conjecture, which tells us somehow, okay, maybe not that these two lines meet, but that if we take this linear programming bounds and take somehow some relaxation of them, then in very big dimensions we can always find the configurations. But it's more like I don't know. I think till now it's more like a belief, because it's very difficult to prove something in big dimensions, especially finding examples.